Imagine standing in a vast, silent cathedral, feeling a deep hum through the floor. By listening to that hum, you could deduce the building's size and shape. This is what astroseismology does for stars. It listens to their vibrations, starquakes, to reveal their hidden interiors. Stars aren't silent, they ring like cosmic bells. Their light carries faint flickers, signatures of sound waves bouncing inside. By measuring these oscillations, we can model a star's interior, from its surface to its core, uncovering secrets of nuclear fusion and stellar evolution. Think of a star as a musical instrument. Its vibrations depend on its size, mass, and composition. Each star sings a unique song, revealing its age, history, and fate. Asteroseismology transforms stars from distant points of light into dynamic, evolving entities with rich inner lives. By interpreting this celestial music, we piece together the universe's story, one stellar heartbeat at a time. It's a profound connection, listening to the heartbeats of the cosmos from across unimaginable distances. The universe becomes a grand orchestra, and we are finally learning to hear its symphony. How do we listen to a star? It starts with understanding how pressure waves, sound waves, travel through stellar interiors. Stars are immense spheres of hot plasma, with nuclear fusion in their cores creating turbulent, boiling motion. This turbulence generates sound waves that propagate outward, bending and reflecting through layers of changing temperature and density. Like seismologists mapping Earth's interior, astronomers use these waves to probe a star's structure. As waves reach the surface, they cause tiny oscillations, making the star's brightness fluctuate ever so slightly. Our telescopes detect these minuscule, periodic changes in brightness. By disentangling the complex mix of frequencies, we build detailed maps of stellar interiors. We can measure the depth of convective layers, core composition, and even pinpoint nuclear burning zones. It's like performing a CAT scan on a star, from light years away. Our Sun is the best-studied star in astroseismology, a field called Helioseismology. Because the Sun is close, we can resolve its surface and watch waves ripple across it, detecting millions of oscillation frequencies. This data lets us measure the Sun's internal rotation, trace flows beneath sunspots, and test stellar models with unmatched precision. For distant stars, we see only a single point of light, limiting us to the simplest global oscillations. It's like hearing the main beat of an orchestra from outside the concert hall, missing the finer details. Despite this, the Sun serves as our calibration point, the Rosetta Stone for understanding all other stars. The physical laws we test on the Sun apply across the galaxy. By refining our theories with solar data, we can confidently interpret the limited signals from distant stars. Helioseismology is the foundation of asteroseismology, extending our knowledge from our solar backyard to the wider universe. The Sun's vibrations unlock the secrets of stars everywhere. Our understanding of the cosmos begins at home, with our own star. The music of stars is a complex harmony of different vibrations, mainly pressure modes and gravity modes. P modes are sound waves. Their restoring force is pressure. They travel throughout the star, especially sensitive to outer layers, and cause rapid flickering in sun-like stars. By analyzing P mode frequencies, we can measure a star's radius, mass, and age with remarkable accuracy. G modes, on the other hand, are slow oscillations driven by buoyancy, sloshing deep within the star's interior. These waves are hard to detect because they barely reach the surface, but they carry precious information from the stellar core. G modes reveal details about core composition and rotation, crucial for understanding stellar evolution. For years, G modes in the Sun were only theoretical, but recent detections are opening new windows into stellar physics. P modes are the loud, clear notes. G modes are the subtle undertones. Together, they form the full symphony of a star's inner life. Each mode tells a different part of the star's story. Unlocking both is key to understanding how stars live and die. The search for G modes is one of astroseismology's greatest quests. The universe hosts a diverse choir of pulsating stars, each with its own rhythm. Cepheid variables are massive, luminous stars that pulsate regularly. Their period-brightness relationship lets us measure cosmic distances. Our Lyrae stars are older, less massive, and pulsate with shorter periods, serving as standard candles in ancient star clusters. Delta Scuti stars, more massive and hotter than the Sun, vibrate with many overlapping modes, offering rich data for stellar models. Even white dwarfs, the remnants of dead stars, can pulsate, their simple structure allowing precise measurements of mass and temperature. Each type of pulsating star reveals unique insights into stellar evolution and the history of our galaxy. Cepheids and RR Lyrae help map the universe's scale. Delta Scuti stars challenge our models with their complexity. White dwarfs show us the final stages of stellar life. Together, these stars form the rhythm section of the cosmic orchestra. What sets a star vibrating? For many, it's the kappa mechanism, a heat engine deep inside where layers of ionized helium trap and release heat, driving rhythmic pulsations. In Cepheids and RR Lyrae, this cycle of trapping and releasing energy causes the entire star to pulse regularly. For stars like the Sun, vibrations are driven by turbulent convection in the outer layers, millions of tiny hammer blows exciting a range of resonant frequencies. The Sun rings constantly from its own internal weather. Some stars vibrate due to external forces, like the gravitational pull of a close companion in binary systems. Tidal forces stretch and squeeze the stars, exciting specific oscillation modes. These tidally induced pulsations reveal not just the star's properties, but also the dynamics of their interactions. Each mechanism adds a new layer to the stellar symphony. The universe's music is played by many hands. Detecting starquakes from Earth was nearly impossible due to atmospheric noise. The breakthrough came with NASA's Kepler space telescope, which stared at 150,000 stars, capturing their subtle flickers with unprecedented precision. Kepler revolutionized asteroseismology, providing long, uninterrupted light curves and revealing the symphonies of thousands of stars. We could suddenly measure stellar ages, radii, and masses with remarkable accuracy. Kepler made asteroseismology a mainstream tool in astrophysics. Its successor, TESS, scans almost the entire sky, cataloging pulsations in millions of nearby stars. TESS's all-sky survey is building a vast database for future studies, mapping stellar heartbeats across the galaxy. These missions are our ears in space, detecting brightness changes as small as a few parts per million. The data they provide, combined with advanced models, turns faint flickers into profound knowledge about stellar interiors. Thanks to Kepler and TESS, the night sky is now a concert hall of cosmic music. What have we learned from asteroseismology? It's transformed stellar physics from theory to precision science. Oscillation frequencies provide thousands of new measurements, refining our models of how stars work. We can now determine a star's age by reading its internal clock, crucial for understanding planetary systems and the timeline for life. Asteroseismology lets us probe extreme physics in stellar cores and white dwarfs, testing our understanding under conditions impossible on Earth. We've discovered, for example, that red giant cores spin much faster than their envelopes, revealing how stars evolve. The technique is vital for exoplanet studies. Knowing a star's size and mass lets us accurately measure its planet's properties. Combining asteroseismology with exoplanet data tells us if a planet is rocky like Earth or a gas giant like Jupiter. Each new insight brings us closer to understanding the diversity of worlds in our galaxy. Asteroseismology is the key to unlocking the secrets of stars and their planets. It's a cosmic detective story, with every vibration a new clue. Starquakes have become one of our most powerful tools for understanding the cosmos, connecting atomic physics to the grand architecture of stars and planets. Every flicker of starlight is a message from a distant furnace, decoded by asteroseismology. Measuring the age of stars with planets helps us piece together the puzzle of life's potential in the universe. The field is entering a golden age, with missions like TESS and the upcoming Plato telescope set to revolutionize our knowledge of sun-like stars and their worlds. By listening to stellar heartbeats, we trace the cycles that create the elements of life and nurture planets. Each new frequency adds a note to the cosmic symphony. The subtle vibrations of distant suns reveal the laws of nature, the history of our galaxy, and our prospects for finding life beyond Earth. The stars are singing, and at last, we're learning the tune.